Molar mass and number of molecules, because this is some longer calculations. So isopentyl acetate is the compound responsible for the scent of bananas, which can be produced commercially. Bees release about 1 microgram of this compound when they sting. The resulting scent attracts other bees to join the attack. Fun times. All right. We want to calculate the number of molecules of isopentyl acetate released in a typical bee sting. What do we need to start with? The 1 microgram, which they very nicely told us is 1 times 10 to the negative 6 grams. As a friendly note on metric prefixes, I and the AP test do not typically expect you to remember things as far as micro. The big ones you must remember, and if you do not know them by now, know them. You better know how to deal with milli. You better know how to deal with kilo. Which one's milli? The small one. How many decimal places do we move? 3. Kilo is? We move the decimal place 3. So both thousandth and thousand are the ones I expect you to be able to deal with. The other ones are mostly just playing around. Those are ones chemistry cares about. All right. So we're going to start with our 1 times 10 to the negative 6 grams. Where do we pretty much always have to get to? Moles. Is moles going to go on top or on bottom? Top. At this point in time, should we have anything other than 1 mole? No. When we get to stoichiometry, that's where you can have things other than 1 mole. For now, unless it's given. All right, molar mass. Anybody got a calculator handy to get us our molar mass? 130.169 grams. All right. If we're trying to get to molecules, we're not done yet because moles and molecules are not the same thing. So where else do I need moles? On the bottom. And what's going to go on top? 10 to the 23rd. And remember, there's not really a good way to abbreviate molecules because typically you're then going to confuse it for moles. We don't go to molecules often. All right, so again, do your math. Make sure that you end up with that. And so to calculate the number of carbon atoms, we would start with our molecules. And we should have units. This is our molecules. A quick reminder on significant figures. Does anyone know why they rounded to 5? What did they give us? 1. How many significant figures does 1 have? 1. So your answer can't have more than that. And remember, in scientific notation, anything you bother to write is significant. The times 10 to the power doesn't matter. It occasionally makes it easier if you're trying to, say your answer is 200, but you should have 2 significant figures. Scientific notation is about the only way to accomplish that, because if you write 200 with no decimal, you have 1 significant figure. If you write 200 with a decimal, you have 3 significant figures. Scientific notation is occasionally just safer. All right, so we got 5 times 10 to the 15th molecules. Where else do we need molecules? On the bottom. How many molecules will this be if we're trying to get to carbon atoms?
1 molecule is 7.
Right, so 1 molecule of, we're just going to call it IA, isopropyl acetate, is going to have how many carbons? 7. Or as Sean Connery would say, 7. That was the entirety of the Sean Connery impersonation my Cal 3 professor could do. It was pretty funny. All right. So 7 carbons. So you just take your 5 times 10 to the 15th, multiply by 7. There we go. So subscripts can be used to determine how many of that type of atom per molecule. And if we're trying to get to molecules or atoms, we're always going to end up having to deal with our 6.02 times 10 to the 23rd. All right, moving on. Percent composition. Do we need to actually work a problem on finding percent composition of a substance? Okay. So, carbone is a substance that occurs in two forms that have different arrangements of atoms with the same molecular formula. For reference, that's an isomer. They're molecules with the same formula but different connectivity. We do not deal with that much in AP chemistry. Raise your hand if you're majoring in either chemistry, biology, or some kind of pre-med, pre-dental, pre-vet, all that. You will have to take organic chemistry. Organic chemistry cares a lot about isomers. That's like half your life. So, well, okay, not really, but for the first bit. All right, so they're going to have, because they have the same formula, they have the same percent composition. How do we find a percent? Somebody other than AJ, because he's answered like 3 things so far. That's if we have a decimal already. What are percents out of? 100 represents how much of the substance? All of it. So it's part over whole times 100. Because one of those things, you found percentages forever, but the last time you had to think about what that actually meant occasionally a while ago. So part over whole times 100. So we have to find it for each substance. We're just going to go ahead and find it for carbon. The rest of them will work the same. So carbon, how much of this substance is just carbon? How many carbons do we have? 10. The mass of one carbon is 12, approximately. We're going to go ahead and put 12.01. So that's the part that is carbon. The whole would be the molar mass. Anybody got calculator handy and has found the molar mass for the entire substance? So adding clarification up top while we're trying to figure that out. Element over molar mass is what we're doing.
It's around 150.22.
Around 150.22.
Got it. And then I truncated it.
Okay. So about 150.22. And so 10 times 12 is going to be about 120. 120 over 150 is going to be about, 2/3. Wait.
4/5.
4/5. So it's going to be 80%, approximately. Yeah, because 3 goes into both. Well, 30 goes into both. All right. And so you do the same thing for your hydrogen, you do the same thing for your oxygen. And if you notice down here, again, try it on your own. If you don't get those, talk to me. All right. Moving on to determining formulas of compounds. Empirical formulas, molecular formulas. So there's a couple definitions up here that you want to make note of. Empirical are the simplest or smallest. Molecular are actual numbers. Empirical you can find with much less information. And if you want to go with some math terms, empirical is our least common multiple. All right. Other things we need to be aware of, hydrates versus anhydrous. The first step we're going to do in lab tomorrow is take off waters of hydration. Waters of hydration are simply water molecules that attach themselves to a compound. Those will be written, for example, one thing we use a lot is copper sulfate, just because we have a ridiculous amount of it. Copper sulfate comes as a pentahydrate. So when you're writing the formula for hydrate, you do compound dot however many waters it comes with. So that'd be copper 2-sulfate pentahydrate. Anhydrous, what's the prefix an mean? Not. So anhydrous means you've taken that water off. All right. Okay. Oh, we'll do the long one. Apparently we don't want to scroll quickly. All right, so exercise 10. Determine the empirical and molecular formulas for a compound that gives the following analysis in mass percents. So if you have mass percents, we said that that's part out of how many? 100. You always need to make it in terms of grams. So grams are something we can do math with. So if we're doing an empirical formula problem, I'm going to change our percent to grams. When we have grams of a substance, what do we pretty much always have to get to? Moles. Friendly note. If you are already in moles, don't change it. Every once in a while, we try to be nice and we give you moles, and then people get that to grams, and life goes badly. So you're going to go to moles. So step 1, change to grams if you have percentages. Step 2, go to moles. Step 3, we're going to find mole ratios. All right, so let's start here. So if we've got 71.65% chlorine, that's now going to be what? What was our first step? So we just put a G instead of the percent. Yeah. Because again, if we had 100 grams of the substance, we would have 71.65 grams of the substance, so it works. All right, and then we need to go to moles. So if this is grams of chlorine, what do I need on the bottom? Grams of chlorine, which in this case should be how many? Okay. When in doubt in empirical molecular formulas, go pretty precisely. 3 places is usually okay. Also, I usually do chlorine to 3 decimal places because it's a palindrome at 3 decimal places. Yeah. And this is per 1 mole of chlorine. All right. So this is not one where we can estimate. This one we have to actually do math. So divide and give me at least 4 decimal places. Mm-hmm. Yes, go get a calculator if you need a calculator.
2.020.
2.02.
Well, 2.021.
Okay. Well, okay, I told you to give me 4 decimal places, not 4 significant figures. Okay. Well, we'll do 99 then. Okay. And so this is moles of Cl. All right, so we'll do the same thing for carbon. So we have 24.27 grams of carbon. I'm going to run out of space. And we need, so if we've got grams of carbon, we need to go to moles, which means we need our molar mass. What's molar mass for carbon? On top is going to be 1 mole. .02 again. Okay. And then for hydrogen, we got 4.07 grams. What's molar mass for hydrogen? Okay. Per 1 mole. Okay. And so what does that get us?
4.037.
All right. And so now you need to know how these compare to each other. So you're going to, that is carbon and not hydrogen. Next step is divide by smallest number of moles. So what's our smallest number of moles? 2.02, so we divide everything by 2.02. Okay. So 2.02 divided by 2.02 is going to be 1, 1, 2. Okay, how close to 2 is it?
1.9985.
That's okay. If you're within a tenth of being a whole number, you can safely round. If you are more than a tenth away, you probably need to multiply. In AP, it will not always work out nicely. You may have to multiply by weird numbers. If it works out to be about 0.8, what should we multiply by? What's the easiest way to get that to a whole number by multiplying? There's a lower one. 5, because 0.8 is going to be 80%, 4/5. If it's any kind of 0.2 multiple, multiply by 5. If it's like 0.65, what would be the easiest thing to multiply, do we think? No, because that's going to get us 0.3 in the end. What's 0.65 close to being? 0.66, which would be what as a fraction? 2/3. Play around with it. There's not really hard and fast rules on that one. You need something that's going to get you a whole number or very, very close to it. There's not usually going to be a lot that get really squirrely on numbers like that. And actually, I think usually on the AP test, they don't go quite that weird. All right, so what is our empirical formula, which it tells us, but did our empirical formula match what it gave us? Yes. By convention, if you've got a carbon, carbon goes first. Hydrogens usually go after that. Everything else goes after that. They usually don't get too picky if you put them in a weird order. All right, so now we need to know our molecular formula. This is going to be molar mass divided by empirical mass, and then that's going to be what you multiply by. So what is the mass of 1 carbon, 2 hydrogens, and a chlorine?
Around 50.
About 50. Be a little more precise than that.
49.35 or 0.45. 49.45.
Okay. So 49.45. What was the molecular mass, molar mass for this compound? 98. So we're going to do 98.96 divided by 49.45, which is going to be work out to right about 2. So if our empirical was CH2Cl, we multiply all of that by 2, which will get us a molecular, empirical by the way, a molecular formula of C how many? 2. All right. So get everything to moles, find your mole ratio using your lowest, get it to whole number if you have to, divide to find your ratio. Yes?
What is 98 point?
This is the grams per mole from our molar mass. That's okay. Somebody else probably had the question. All right, I'm hoping to find one. Let's see. Oh, really? Does it not do? I wanted to do a waters of hydration problem, and apparently there's not a waters of hydration problem. Pooh. The other one you have to watch out for is sometimes it will tell you how much carbon dioxide and water get made. You have to convert those to moles of things. I apparently do not have examples of those handy. I will try to find some, and if I can find them by the end of class, we'll work them before the end of class. For right now, though, work on your quest or start reading your lab for tomorrow.